Okay, let's begin talking about ecology. Specifically, this is the first video in the ecology unit. So, what is ecology? Ecology is the study of the interaction of organisms, not only with other organisms, but also with their physical environment. We're going to talk more about the physical environment in a little while. Habitat. Well, we have to have a vocabulary word for that, and that is literally the place where the organism lives. Okay, so what is the difference between a population and a community? Well, a population is all of the individuals of a particular species. Okay, so a community is going to be more than one species. So for example, if I was talking about a population, I could refer to the population of Homo sapiens sapiens that are in my classroom. Right? We're all Homo sapiens. We're one species. We interact with each other. So I could define that as a population. But I could also talk about my classroom being a community as well, because not only are there Homo sapiens, which is one particular species in my classroom, there are also different kinds of plants, different kinds of microbes, like bacteria. I hope not, but possibly some insects, or arthropods. So when we talk about a population, we're referring to a single species of interacting organisms, and in a community, we're referring to more than just one species. So that's real important to know the difference between those. An ecosystem is not only the community, which is various species interacting, but also we want to talk about the fact that an ecosystem is going to deal with those abiotic factors as well, like water, light, heat, soil, air. Okay, so these would be the types of abiotic factors that are involved in an ecosystem. And then ultimately the biosphere literally means life ball, and that is going to be all the communities on Earth whose members exist not only on terrestrial Earth, land, but also aquatic and atmospheric. So those that live, in the air, on the land, and in the water. So there's some vocabulary words that we've got to start out with so that we know what each other's talking about. So when we think of ecological levels, you have to kind of define what are you talking about. Are we talking about a single organism, i.e. this fish? Or are we talking about a population of that particular species of fish? Or are we talking about the community that that species of fish lives in with other species? Or are we ultimately talking about not only the different species interacting, but also the atmosphere and the oceanic, in this case, abiotic factors that would be involved as well? So what is demography? Demography is the statistical study of a population. I mean, let's face it, scientists like to keep data. We like to keep numbers. We like to have numerical data that actually describes things, not just in terms of feel-good words, but numerically, and so that's very important to us. So when we think of demography, we want to think about, how populated, how close together, what is the density of this particular population? How is this population distributed? How is this population growing? Are they growing at a logical rate, or are they growing at an exponential rate? Are they dying logistically, or is there something causing them to die at a larger number than are being produced? And so these are things that scientists would want to look into. We would want to also think about things like, when I mentioned density, are they clumped, distributed, or is there a high density? Let me give an example. In the United States, when you look at the United States from out in space, and we look down at the United States in terms of light being emitted, well, obviously we can clearly see where the coast is, right? The West Coast, the East Coast, Florida. You can clearly see where your large cities are. But if you look out west, kind of in what we call the flyover states, you'll notice that the light distribution is not as great. Well, that kind of indicates to us that the population is not as high in those areas as it is, say, in your metropolitan New York or anything along the coast. So when we're looking at density, we want to know, how many people, or not people, but how many of that particular organism are there, how are they distributed, and is there anything in their environment that's going to limit their growth? Okay, well, speaking of growth, this is kind of pretty easy. The rate of natural increase depends on how many people, or again, I keep saying people, I apologize, but how many individuals are born and how many individuals die each year. So this is going to indicate growth. When we think about growth, we often refer to something as biotic potential, life potential. And life potential or biotic potential is defined as the maximum rate of natural increase for a population that can occur when resources are what? Unlimited. In other words, the organism has everything that it could possibly need. And if it had everything it could possibly need, what is the maximum rate of increase that we would see? So what kind of factors would influence biotic potential? Well, usually you think of things like, well, how many offspring are they going to have? What is the chance that their offspring are actually going to survive until they're able to reproduce? And then another thing that's important is, well, how often do they reproduce? So, for example, for humans, Homo sapiens, we reproduce in 9 months or 40 weeks. And again, I could explain that, but that'll be later. But basically 9-month gestation period, whereas like a fly or a mouse may have a very short reproduction age. In other words, it only takes a few weeks before they're sexually mature and they can reproduce. So these are some factors that we look into. And then, of course, the last thing is we want to say, well, what age does reproduction begin? Right? So for us, we look at, for humans, we look at, well, what is the onset of puberty? Now, I don't advise that being the age that they could reproduce, but technically, for example, with females, they cannot reproduce until they have reached menses. So, again, we're looking at age, and again, with a mouse or something like that, it may just be a matter of, 2 weeks, and then they're capable of producing offspring. So in this particular image here, look at the biotic potential of, say, this sow with her piglets opposed to this, and I think these are referred to as cows, with the rhinoceros and its offsprings. Notice the difference. The one on the left has a large number of offspring. If you look at the food source, domestication, the farmer's going to take care of it, provide for it. It has a much higher biotic potential than, say, the rhinoceros. Thus, the rhinoceros produces just one, limited food availability, protection. So again, they would have a lower biotic potential than, say, the pig or the sow on the left-hand side. Well, another thing we look at when we're thinking about populations is we look at mortality patterns. And a term that's often used is, a cohort. And a cohort just basically means any organism or a member of a population that is born at the same time as others. So, for example, you and your classmates would be cohorts of each other, whereas maybe me and your parents, we would be better defined as cohorts. We also look at survivorship. We actually look at, what's the probability that that newborn is actually going to survive to old age. And so what we often do is we interpret survivorship curves. And so if we look at these examples here, right, let's think about grasses. Let's think about springtime, summer, grasses. Large number of individuals or organisms are, I hate to say born, but we'll use that term, born. They live throughout their lifespan. They live most of their lifespan. And then they all tend to decrease at about the same time. Well, we would define that, as one type of survivorship curve, and in this case it's survivorship 1. Not that you have to know that, but it's a survivorship 1 curve. If you look at the iguana, or the reptile down here in the bottom left, the lizard, we clearly see that is a that the death is not related to age. It seems to die off at a logical or logistical manner. Right? You start out with the number of population and they kind of die equally throughout their lifetime, okay? And then the third type is like in the case of your arthropods, your insects and things like that, mosquitoes, they're born, but death comes on early. Like, so compared to the number that were actually laid versus hatching and live to all the way throughout their lifespan, it's very different. So again, scientists look at these things, and it helps us to kind of know what's going on in the environment, and we can kind of tell based on these curves, what kind of survivability that each type of organism might have. We also look at age distribution, and there's three major age groups that we look at. Are these pre-reproductive, are they reproductive, or are they post-reproductive? And so often we will look again at a diagram, and based on that diagram we're able to kind of predict what's going to happen in that environment. So if you look at the first one, clearly you see that there's a large number of pre-reproductive ages. Well, what does that mean? If we're talking about humans, we're talking about there's a lot of offspring. Okay, and notice that that's going to be in a country where they produce incredible numbers of offspring, but if you look, the number that actually make it to post-reproductive age, or as I would call it, old age, is not nearly what they started out with. Okay, a stable population, this would kind of be like, say the United States. If you think about it, two parents produce two offspring. So the number that are pre-reproductive is kind of similar to what we're going to see at post-reproductive ages. And then in the far right one, we see a decreasing population, and that's one where they have chosen, again I'm using humans, but they've chosen to restrict the number of offspring or pre-reproductive age organisms. And so you'll kind of notice that the graph or the diagram is kind of skewed. It's kind of disproportionate. So you have a lot that are in the reproductive age and post-reproductive, but not that many offspring being made. So again, these are things that scientists look at to kind of gauge the health of that particular ecosystem. Logistical growth occurs when environmental resistance retards exponential growth. What does that mean, Ms. Bradley? It basically means that things in the environment are going to keep you just from going crazy and producing uncontrollable or unsustainable numbers. And remember that populations will eventually come under control of environmental resistance. And again, we'll talk more about that, especially when I talk about, say, deer and deer populations, or when things get out of control, and then what tends to happen to get them back into the proper numbers that they should be. Well, with that being said, that then leads me to carrying capacity, and this is in my opinion, a very important concept, because it basically says this is the maximum number of individuals of a species that the environment can continuously support, right? So continuously support, the maximum number of individuals that the species of that environment can continuously support. And notice I have in red that the closer the population gets to the carrying capacity, the greater the environmental resistance. What does that mean? It means basically that the environment fights back. So when we're looking at population size, we can look at two major types of factors that will help regulate that. Some are called density independent factors. Density independent. Independent, you can't control it. Okay, independent. And so this would be things like natural disasters. We cannot control a hurricane. We cannot control lightning strikes that cause forest fires. We cannot control tornadoes, tornadic activity, earthquakes, tsunamis. These are things that unfortunately do reduce numbers of organisms in a particular environment, but we have no control over those. Oftentimes those are referred to as acts of God. Okay, these are things that we cannot control. But we also know that there are some things, density-dependent factors, that the percent of the population affected increases when the population density increases. So what do we know when things start getting crowded? Well, we know that there becomes more competition. Well, competition will often lead to predation, right? Predator-preys, predators eating prey, and then parasitism. Right? One organism mooching off the other. So again, these are factors that play into that. So if you'll remember, I mentioned something about deer, and so let's look at this for example. This is caribou, these are reindeer, and noticing some data that had been kept 1910 to 1950, and noticed that the number of reindeer in this particular area that it was being studied was starting to show, it was kind of a slow growth, but then all of a sudden about 1930 they saw exponential growth, and wow, the population went to 2,000. But notice that as that population began to grow and grow and grow and grow, the environment fought back and said, there's not enough resources to sustain this kind of population, and so clearly you see a crash occur. And then what happened then after 1950, then that it maybe didn't go all the way to zero, but it began to level out, and then you start to see growth again. But again, the environment can't support unlimited numbers, and so that's an example of how the carrying capacity must be maintained. I mentioned competition. When you start crowding a lot of organisms or a particular population in an area, there begins to be competition. Well, competition is going to drive predator-prey relationships. So again, that's kind of, in this picture, if you have a low density of mice, you're not going to have that many hawks. Well, the more mice there are, the more hawks that are going to be in that area, which is going to reduce the number of mice, which, and so it's very cyclic in nature. Okay, life history patterns. Well, one of the things, okay, here's some vocabulary words. There's something called fecundity, and that's the number of births per population, per reproduction. So, how many do most humans have? They typically have one per reproductive event. Maturity, what's the age of reproduction? How old are they before they're able to produce offspring? And then parity, how many births can they have in a year? So again, for humans, we typically can have one birth event, reproductive event per year, because our gestation is 9 months long. We also refer to life history patterns, excuse me, I'm stumbling, but are you an R strategist or a K strategist? So R strategists are kind of known as opportunistic species. Think of mice, think of weeds, think of think of organisms that are very opportunistic. They're typically going to have large number of offsprings. They're typically going to be very small in size. They're going to have sexual maturity early. They typically don't live very long, short lifespan. They typically don't take care of their young, or if so, it's very limited care of their young. And they tend to be excellent dispersers and colonizers. Your K strategists are known as equilibrium species. This would be more like us. We tend to produce, small numbers of offspring. We typically have a larger body size. Sexual maturation occurs late. We typically have a long lifespan. We invest energy in taking care of our young. We tend to be great competitors, and we often are very specialized in our ecosystem. We're very specialized as to what we do. And so again, when you're thinking of organisms, are they opportunistic, or are they more sustainable or equilibrium? Are they an R strategist or a K strategist? And these are things that you would want to think about as well. And so one of the things I ask you to do is, is to look at the, ecology focus. When does a population grow too large? And this is something that we see in our area. White-tailed deer are prolific breeders. They breed their first year, and once they start, they have about 2 young every year. And what we notice is that about a century ago, there was less than 500,000. And today there's over 200 million white-tailed deer. Well, why? Why such an increase? Well, think about it. Wolves and mountain lions have been eradicated from areas. Their natural predators have been removed. We know that when these populations get too large, because of the food supply being limited, we know that they often get sick. We know that hunting, is not as prevalent as it used to be back when it was a necessity to be able to eat. And so, you just have to think that as much as we love seeing Bambi and, we love seeing these, then when their populations get too large, they start running out into the road. They, because their habitat is being restricted, and then you see them starting to get sick. And so the bottom line is that ecology, nature, tries to maintain homeostasis. It tries to maintain balance. Speaking of growth, human population, we expect that the human population is going to double every 52 years. So basically, when we look at the population size, in the year 2000, it was 6 billion people, right? So we're kind of predicting that by 2050, because I think the number keeps coming down, but by 2050, we'll be 12 billion people on planet Earth. And I want you to think of the resources: water, food, shelter. Think about this. Where are we going to put them? And are we going to see the same type of thing happen to the human population that we see to that deer population if it goes unchecked? And as we kind of wrap up this particular section, very often, I'm sure you've heard of third world countries or, superpowers, but today we call them more developed and less developed countries. And when we think about your more developed countries, that's going to be things like North America, Europe, Japan, Australia. Typically, you're going to see a slow growth pattern. We don't typically grow super large. We're large, but we don't grow at an exaggerated rate. We typically have a high standard of living. We typically see that the death rate is not as great as in some of your less developed countries. We also see that birth rates tend to be controlled. So we typically see a stabilized population in these more developed countries. In your less developed countries, however, these are going to be like Latin America, Africa, and Asia. You're going to see rapid population growth, typically a lower standard of living. And so one of the things that we look at is we think of, what kind of strategies could we help them with to help reduce population growth? And so you hear all these things about, family planning programs, basically birth control, or how to control the number of offspring you choose to have, social progress, which may result in reducing the desire for a large family, delaying childbearing. For us, we would kind of sit there and go, wow, 12 years old, 13 years old, that's entirely too young to, be a mother. But in some countries, that's, once menses has begun, then they see that that child or that young woman is eligible to be married, and thus can begin child raising. And so again, remember that there's no right or wrong, there's just different. But remember that these I said organisms, but this population is going to continue to grow, and we want to think of ways that we could possibly help with that. Again, standard of living is very, very different. Look at the difference in the age diagrams. This is more in your more developed countries. This is more in your less developed countries. But again, look at how many make it to, old age. The old age number is the same, but look at the number that they started out with. So again, these are things that we have to consider. We have to think about, even if they're not fun to think about. And then finally, as I wrap this part up, what's the environmental impact of population size, resource consumption per capita, that means per person, pollution, right? So, we use these resources, but what happens, there's pollution, there's waste product. And so one of the things I love to show is that this graph, that even though the less developed countries may have the greater population compared to your more developed, look at the countries that produce the most hazardous waste, use the most fossil fuels, use the most metal, the most paper. Guys, our consumption as more developed countries far exceeds those of those less developed countries, and we have to ask ourselves then, where does the responsibility lie? Alright, so that's where I'm going to stop for this video, and I'll pick up with the next video in a moment.